So now let's analyze Dijkstra's algorithm for the single source shortest path problem. So recall that Dijkstra's algorithm operates by burning vertices in the analogy we used. So we keep track of vertices which have been burnt or visited. Initially nothing is visited, and initially we don't know any distance to any vertex, so we assume all distances are at infinity. Then we start at the source vertex, let us call it 1 by assumption. So we set its distance to 0. Then we repeatedly pick up the first vertex which is not burnt and which has the minimum distance among those which are not burnt, visit it and recompute the distance to all its neighbors. So before we look at the complexity of this algorithm, we actually first have to verify that it is correct. So Dijkstra's algorithm now makes a sequence of updates. It is a bit analogous to BFS or DFS because it keeps visiting vertices and it visits every vertex only once. Now it visits vertices in a particular order which is different from breadth first or depth first, and we need to justify that this order is actually correct. So in some sense, at every point, breadth first search looks at all its neighbors and visits them, say, in the order of their vertex number. Depth first search will pick the first neighbor and then explore it further. Now Dijkstra's algorithm uses a different strategy, which is to pick the smallest distance unvisited neighbor. So we have to justify that this choice, which is never undone, that is, you keep going forward and you never go back and say, oh, maybe I should have chosen a different one, that this kind of a strategy actually is correct. So this is a general class of algorithms called greedy algorithms, where you have a number of possible trajectories or paths that you can choose to solve the problem. At each stage, you make the next choice based on some local information. At this point, this looks like the best choice to make. And then somehow, magically, this best choice that you make on local information turns out to be globally the best trajectory to take. So for such greedy algorithms, it's important to establish that this local choice of the next step actually gives us a global optimum, because very often this kind of a local heuristic does not give us a correct algorithm. So let's first look at the correctness of Dijkstra's algorithm. So the key to establishing correctness in this particular case is to establish what is called an invariant. Right? So now Dijkstra's algorithm proceeds, as we saw, in a sequence of iterations. There are n iterations. The invariant is that at each iteration we have this characterization of vertices as burnt and unburnt, and what we want to claim is that the burnt vertices are correctly solved. That is, at any point, if we look at the distances assigned to the vertices in the burnt set, then those distances are actually the shortest distances from the source vertex to that burnt vertex. So if we assume that this inductive invariant is true, now it is certainly true at the beginning, because right at the beginning the only vertex that we have burnt is the start vertex S. Right? So the first vertex we burn is S and we set its distance to 0. So certainly at that point this property is true, that among the burnt vertices the distances are in fact the shortest distances. Now assuming that we have extended the set for a few vertices, now we want to add a new one. So what we said is that we will pick a vertex V, okay, such that if we look at the distance to X plus the weight of X V, if you look at this total sum, which will be the updated distance to V, this is smallest among all the vertices which are not burnt. So the claim is that if we now add this to our burnt set, right, so if we extend our burnt set like this to include V, then the distance to V cannot be actually smaller than what we have computed now, and it will not change because of a later update. So how will it change because of a later update? It could be that at some later point we actually extend our burnt set to include a new W. Now, can it be that there was a path from Y to W to V which is shorter than the path we have claimed just now via X to V? So it's easy to see that the distance to Y plus the cost of WXY, now this must be bigger than or equal to the earlier thing, because we chose V and not W, because at this point W was not the smallest one, V was. Now perhaps they were equal, but certainly W was not less than V. So at a later stage, if we go to W, we know that we will take at least that much time to reach W, and then we have to additionally incur a cost of going from W to V. So there is no way that a later path that we can discover via Y to W to V can be better than the current path from X to V. Right? So this re-establishes the invariant that the vertex we burn next is correctly solved. So this is a way to show that Dijkstra's greedy strategy actually solves this problem correctly. So now, having established that it is correct, let us look at the complexity. So there are some obvious loops in this. So there is an order n loop of initializing the visited values to false and the distances to infinity. Now there is another order n loop here, okay? And inside this order n loop, there are two loops. One is more obvious than the other. So here, once we have visited a vertex, a new vertex, then we have to go through all its outgoing neighbors, right? So there is a scan of all edges which are going out of U. So that is one loop. But also there is a loop here which is kind of implicit, which is before we visit a vertex, we have to choose it, right? So we have to go through all the unvisited vertices and pick the one whose distance is minimum. So this, in general, we have seen that if we have a list or an array which is not in any particular order, then to find the minimum, we may have to scan the entire array. So this is implicitly an order n step. So this is an order n step, and the time it takes here depends on how we represent the edges. Right? So the outer loop runs n times, as we saw. In each iteration, we burn one vertex. This requires an order n scan to find the minimum vertex to burn. After we burn the vertex, we have to scan its neighbors to update the burn times of those vertices. Now, if we have an adjacency matrix, as we have seen, then if we are going to burn U now, then in order to find its neighbors, we have to scan the row for U in the adjacency matrix. So this will take order n time. Right? So we have an outer order n, and inside we have two order n things independent of each other. One is to find the minimum unburnt vertex to burn next, and second is to update all its neighbors. Right? So because we have this order n thing inside an order n loop, overall it is order n square. So now, one of the bottlenecks certainly is this adjacency matrix, right? So we have seen in BFS and DFS that if we move from an adjacency matrix to an adjacency list, scanning all the vertices of a particular, all the neighbors of a particular vertex becomes more efficient. So we can do the same thing here, right? So if we move from an adjacency matrix to an adjacency list representation, certainly the second order n loop within each iteration can be now counted as an overall order m cost, because across all the iterations we will explore every edge only once, because we will explore it when we burn its source vertex. Right? So therefore, the second contribution of order n gets solved by using an adjacency list, but unfortunately, we still have the first order n step, which is to find the minimum. So we have a list of burn times associated with the unvisited vertices, and we have to find the minimum among them, and this remains an order n step. So overall, though we have moved to an adjacency list, this alone does not help us, because we still have an order n step inside the big loop. So we are still at order n squared. So actually, to get around this bottleneck, we need to maintain the burn times in a more sophisticated data structure. So it turns out that we need data structure in which we can, of course, find and remove the minimum element quickly. But once we have that, we also need to be able to update the values quickly, so that overall both updating and extracting are roughly equally the same. So this can be done using a tree-like structure. In particular, we will see in a later lecture that there is a nice data structure called a heap, which precisely allows us to do these two operations in log n time. So if you have n values, then in log n time you can find and delete the minimum value, and we can insert a new value or update a value which is already in the heap. All these operations take only log n time. So if this, which we will see later, if this can be done, then what it says is that finding the minimum burn time takes log n time. Now when we update the vertices which are adjacent to the current burnt vertex, overall we do this OM times, right, because there are OM edges, but each update again takes O log n time. So we have now two contributions to our complexity. So this comes from choosing the minimum vertex, right? So in order to extract the minimum vertex, we do this n times, and each time it costs us log n time. And then in order to update the distances once we burn a vertex, each time it takes us log n time, but we do this for each edge, so it's m log n. So we have n log n for choosing a vertex, and this is for updating the distance. Right? So overall, our algorithm becomes n plus m log n. So remember that in a graph, n plus m is really is the size of the graph. So this is really an n log n algorithm, as opposed to the naive O n square. And we have seen in sorting and other such problems that this is a huge practical jump going from O n square to n log n. It's a huge jump in terms of the size of the problem we can hope to solve. So Dijkstra's algorithm makes a very crucial assumption which underlies the correctness of its greedy step, and that is that there is no negative cost associated with an edge. Okay? Our argument was that if we choose V as the next neighbor to add to our bird set, then we can never find a shorter path coming this way. But obviously, if we have negative edges, then we could have a situation where I had, say, a path of length 2 here, right? And then I chose not to follow another path because maybe it is of length 4. But if I come back from there, right, maybe this has length -3. So if I come around this way, then I incur a net cost of only +1, whereas if I go this way, I get +2. Right? So therefore, by locally looking for the nearest neighbor, I don't necessarily find the shortest distance. So now, of course, you might ask why you would want to put negative weights in a graph at all. Well, remember that graphs are a very general model, and there are many situations where you can actually interpret negative weights in a sensible way. So supposing we are looking at, say, a taxi driver, and we are looking at a graph as a list of places where he picks up and drops off people. Now, obviously, there are segments where a passenger is in the car, and there are segments where he may not have to be, may not have a passenger. He may have to just be returning to a place to pick up. For instance, a taxi driver who operates from the airport might typically go back to the airport after every trip because he expects to find longer trips from there and within the city, right? So there are segments where he travels empty, there are segments where he has passengers. So some segments earn money, some segments lose money. So there are some positive edges and there are some negative edges. Another situation which is completely unrelated to anything we have seen so far, you can think of, say, chemical compounds, and we can represent a graph saying how we can transform one compound to another compound. And here, for instance, the edge weight can represent the energy which is either released or absorbed in this process. So again, it could be positive or negative, right? So there are many situations in which negative edge weights actually make sense. So what do we do if we have negative edge weights? So the first thing to notice is that if you have a negative cycle, okay, so if I have a graph in which I have, say, a loop like this, and all of the things add up, say, -3, -2, and +1. Then if I go around the cycle once, right, and come back, then I will incur a total cost of -4. So this means that if I had a path which started somewhere else, came here and left the cycle and went somewhere else, so supposing I had a source and a target, then I can make the distance from the source to target arbitrarily small by going round and round this loop any number of times. At each time I go around the loop, the cost reduces by 4. So I keep adding -4 to my cost. So the cost can be as low as I want, just depending on how many times I go around the loop. So if I have negative cycles in a graph, the question of a shortest path doesn't even make sense. I mean, there's no notion of a shortest path because the quantity is not well defined. But it turns out that if I rule out this, I could have negative edges but not negative cycles. So for instance here, if instead of +1, okay, I said that this was +7. Right? If I make this weight +7, and going around this cycle will cost me +2. So therefore it doesn't help me to go around the cycle because it will only add to my cost. So therefore, in a situation where I have no negative cycles but I do have negative edges, it still makes sense to talk of shortest paths. And we will see later that there are other algorithms other than Dijkstra's algorithm which can handle these. In particular, we will look at the Bellman-Ford algorithm, and we will also see that the all pairs shortest path problem, which generalizes the single source shortest path problem, called the Floyd-Warshall algorithm, will also solve this thing regardless of whether the paths are negative or the weights are negative or not, provided there are no negative cycles.